Now let's look at the process of estimation. How do you come up with the best possible estimate for the slope coefficients? So we have the y values. Y sub I is the ith observation of the response variable or target variable. And then given a combination of x values, then we come up with an estimate y hat sub I. So now the difference between y sub I and y hat sub I is our error. And our objective is to come up with estimated values for all these b coefficients such that this sum of squared error, y minus y sub I hat squared, so it's an error squared, that is the minimum. So that's why it's called least squares estimation. So one more way of looking at these error terms is here. Okay, we start with let's assume that there is only one predictor variable x. Okay, so our discussion will be easier to understand. So we have the y variable here and we have the x variable here, right? We have a scatter plot. For one moment, let's assume that we are not going to look at x at all. We're going to just look at y value and try to predict what the estimate the value of new y. So one approach is to just take all the different y values and average them and use the average value of y as our predicted value. So y bar, right? So we have y bar and that's our prediction. So if that's what we're going to use as prediction, then what is the sum of squares of error that we talked about in the previous slide? So for each possible value of y, the error is going to be the difference between the y value and the y bar value. Some of them will be negative, some of them will be positive. So for example, here for this particular y, this is your y bar. So y sub I minus y bar, so that is the error. Now if we take the error and square it, because some of them will be positive, some of them will be negative, square it and add them up, add all of them up, all the y minus y bars up, then what we get is SST, the total sum of squares. Now we bring in the x variable. So let's figure out an equation between y and x. So it's a straight line, b sub 0 plus b sub 1 x. So let's assume that that's the line. Okay. Now let's go back to this particular x value for which this is the actual y. Now this regression line is going to give you a y hat, a different estimate. We are not going to use y bar anymore. We're going to use this line, which will reduce the amount of error. So this error is going to be smaller than total sum of squares, right? So for each value of actual y, you will have a y hat sub I coming from this green line. Okay. So let's look at this one again. Now what has happened is, without the green line, the error was this, y minus y bar. Now with the green line, so y hat is that, so this is the difference. So this is the error. So this part, which was originally an error, is no longer an error. Okay, so that part is y hat minus y bar. And if you square them for each and every one of these points and add them up, that is called sum of squares of regression. So this gives us an estimate of how much of the original error there was, how much of it is no longer an error, it has been explained by the regression. So that's why we call this sum of squares due to regression, or you can even say explained by regression. So this is a good sum of squares. You want this to be as high as possible. Now what is left over, that is your error. So you have the actual y minus y hat, and if you square them and add them up, you get sum of squares due to error. So because of some mathematical properties, this original sum of squares, total sum of squares, will be the sum of these two squares. So if you add these two, it will be equal to that. So SST will be equal to SSR plus SSE. So our task is to figure out the B coefficients, B sub 0 through B sub P, such that this error terms SSE is the minimum. Okay, now in this slide we're going to look at how to assemble the sum of squares that we calculated before. Okay, so we have the three sums of squares with this relationship SST equal to SSR plus SSE. So we're going to assemble them into what is called ANOVA table. So we have regression, error and total. So we have SST going here, SSE and SSR. Now the degrees of freedom for these, so for the total sum of squares, degrees of freedom is n minus 1, n being the sample size. For regression, the degrees of freedom is p. So how many x's, how many predictors there are. So then these two columns, the two numbers for the source should add up to the total. So if you add SSR and SSC, that will be SST. If you add these two degrees of freedom, and that should be equal to the total degrees of freedom. Now we divide the degrees of freedom into the sum of squares and you get mean square. So this is mean square R and mean square L, MSE, and then that's MSR, and the ratio between MSR and MSC gives you the F statistic to do an F test, and we will look at F test when we look at a numerical example. Now if you take the sum of squares SSR and divide by the SST, what you get is called coefficient of determination, R squared. Okay, the R squared value, it is a squared value, it's a value between 0 and 1. 0 will be the case if SSR is 0, then you get 0 over SST, so the regression model is completely bad, right? Now if the regression model explains the entire error, so SSC is 0, then SSR will be equal to SST, so this value will be equal to 1. So it's a value between 0 and 1. It measures the goodness of fit, and it is a proportion of, you have the total sum of squares, which represents the total variability in the target variable, and this ratio tells us what proportion of that total sum of squares has been explained by the regression. So that is R squared. Now R squared will always go up as P increases. As more and more variable comes in, SSR will only go up and SSC will only go down. Okay. It may not go up by very much, but it will go up. And therefore coefficient determination is not a good measure to understand whether bringing in a new variable is worth it or not, because when you bring in new variable, P will go up, so which means the degrees of freedom here will go down. So your MSC, if the loss of degrees of freedom is not is not compensated by sufficient amount of reduction in SSE, the MSE may go up. So it may not be a good idea. So that is to look at just R squared. So that's the reason why we have adjusted R squared, which adjusts for the fact that when you add new variables, you lose some degrees of freedom, and that may not be worth the reduction in SSC that we may achieve.